In the previous video, we saw the relationship between the height of a tree as well as the number of nodes. In this video, I'm going to make a claim that this height actually depends on the order of insertion. So let's say if we have three elements like 1, 2, and 3, if we try to insert this in a new tree, if we try to insert it in this order, the tree would look something like this, which is 1, and then 2 is on the left of right of 1, 3 is going to be on the right of 2, and the tree would look like this. But let's say if I change the order to something like 2, 1, 3, then our tree would look something like this, which is 2 is the root, 1 will be on the left, and 3 will be on the right. So our tree is more bushy in case like if we have the order like this, while it's more spindly if our order is something like this. So if we try to insert elements in a tree, there are n different elements. There are basically n factorial different ways to insert elements, which is you can insert elements as 1, 2, 3. Then you can have 1, 3, 2, 2, 1, 3, 2, 3, 2. Basically, I'm fixing ones and twos, and then I'm going to fix threes, and then threes will be 1, 2, and 3, 2, 1. So there are 6 different ways for 3 elements. And if we talk about like 4 elements, there'll be 4 factorial ways, which is like 24. So in this case, like if I try to insert trees in elements which are in sorted order, it's going to be more spindly. So these similar elements, if they are inserted into a tree, the trees can look very different. That's the key takeaway of this. And that's why our performance of different operations like insert, delete, and search, in the worst case, depends on how the tree is structured, which is like, let's say if our tree was more spindly or it looked something like this, then to find out like let's say if we wanted to do an insertion in this particular tree, like let's call our insertion number 100, you have to traverse the entire tree without skipping any particular levels and then attach 100 at its end. So the worst case would be dependent on O of h, but h is proportional to O of n, because in this case, like from our previous video, we learned that the minimum number of nodes in such a case is like n, and since our tree is highly skewed, this would be our h is directly proportional to n. So typically in the worst case, our complexity would be something like O of h. And all common operations require O of h complexity, because when we are talking about binary search trees, let's say if we want to search an element, uh, we can skip to lefts and rights, but basically like if you are trying to search an element, you are basically traversing from the root node to a leaf node, a path to find a particular element, and which is directly proportional to the height. So this height in the worst case turns out to be directly proportional to n. So that's why all common operations require O of n complexity in the worst case. When we talk about the average case, there's actually a proof that when we randomly insert numbers in a tree, the height of the tree is proportional to log of n. It's not proportional to n, but it's proportional to log of n. So all common operations can actually be executed in O of log n. So the proof is shown here. It's a very extensive proof, like it's about 30 pages. I won't cover anything related to it. It's too mathematical and beyond the scope of the course. But the key idea is, if in the average case, BSTs have time complexity that is proportional to log of n. So all common operations, whether it's insert, delete, or search, will be proportional to O of log n. Finally, when we talk about the best case, the height in the best case would be something like the minimum height that's possible uh, for the maximum number of nodes, which is, let's say if our nodes was n, if we have, in our best case, the height would be proportional to log of n, because we want it to be as bushy as possible. So our height would be log of n. But when we talk about common operations like finding an element, so in the best case, we can think about it as we found the element at the first place, which was the root node, then we get O of 1 complexity. Or let's say if we are trying to insert an element and there's just one node in the tree, that's the root node, or the tree is empty, then it's going to be O of 1. Similarly, when we are trying to delete an element and there's just one node in the tree, it's going to be O of 1, because we do not have to search anything. We just found the first element right there. So in the best case, the height is proportional to log n, while in the worst case, height is actually equal to n. So it's all height that we are concerned about. So the question to ask is, how can we fix the worst case, which is like, let's say if you have a very spindly tree, how can we fix this? So there are two different approaches, and this week we are going to focus on both of these approaches. The first approach is we never add a new leaf at the bottom. So let's say if we try to insert 100, so instead of adding it as a new leaf, we increase the size of this node, which is we can create like a vector or any particular container that stores like 100. So in that case, let's say if we now insert 101, we keep adding to this container. So this principle of increasing the size of the nodes is used in something called B trees, which we are going to discuss in the next set of videos. In today's videos, we are going to discuss the second principle on how we can fix this, which is we can transform this spindly tree into a bushy tree by using some tools and some algorithms. The tools we are going to discuss is something called rotations, and the algorithms we are going to discuss is, the first one is AVL tree, which we are going to discuss today, and the second one is like red black tree, which we are going to discuss next week in the next set of videos. So let's discuss the first tool that we have, which is if we try to change this entire tree into some other, like we transform this tree into another orientation, can we fix this problem? And that's going to be our topic for the next video.